Welcome to SNC's Power Up webinar on DoD energy installations and utility interconnections. My name is Spencer Zirkelbach, and I will be your host for today's webinar and want to start off by saying thank you to everyone who has joined us today. We have a wide range of attendees from the U.S. Department of Defense, investor-owned utilities, public power utilities, and consultancies. We want to make this webinar a great use of your time, which we believe starts with getting our audience's input on today's topic. And we will be doing this through a few polls during the webinar that we encourage all of our participants to take part in. We're going to start right away, and we would like to get your perspectives on what you feel is the most critical consideration when planning for a new DoD energy installation. I'm launching a poll right now, and I've shared the questions with you all to respond to. As you answer that, I have a few administrative items to cover. First of all, this webinar is being recorded, and a recording will be shared after the event along with a brief survey. We would greatly appreciate a few seconds of your time to provide feedback on today's content. Attendee microphones are muted, and we have turned off the chat feature. Please use the Q&A function at the bottom of the screen to ask any questions you have throughout this webinar. We will address all questions at the end. Finally, if you're having any technical difficulties, you can also use the Q&A function and a member of the SNC team will help. Now that we have those out of the way, let me introduce our panelists who will be sharing their expertise with us today. Emily Lejeune is SNC's business leader for federal customers and brings over 16 years of experience serving the power reliability and resiliency needs for the Department of Defense and other U.S. federal government agencies. Michael Higginson is the Manager of Engineering Services for SNC Electric Company, where he leads consulting and analysis services for distribution systems. Michael is active in both IEEE and SIGRE power system relay committees and has published numerous papers on power resiliency and reliability. Michael is also a licensed professional engineer, and his innovative work has earned 2 patents. Finally, we are very pleased to have Bill Taylor as part of this discussion, who is the director of the Engineering Center of Excellence for Energy Systems Group. In this important role, he leverages over 35 years of industry experience toward the development of advanced energy-based solutions for federal installations, municipalities, universities, schools, and hospitals. Bill, thank you for joining us today. And again, thank you to all of our panelists for sharing their time with this group. Now I'm going to share the poll results and turn it over to Emily for her thoughts on everybody's response. Emily?
Thank you, Spencer. Appreciate you sharing the poll with me, and I appreciate everybody participating. So good morning or good afternoon, everyone, for wherever you are residing. I appreciate you participating in this first poll about what you feel is the most critical consideration. So we gave you a few choices of resiliency, redundancy, distributed energy resources, and existing assets. And it looks like resiliency is winning at 67%. What I love about all of these answers are, I'm hoping that you'll see as we go through today that there's going to be, we're going to touch on a lot of these. So I'm hoping that you'll start seeing some of this as well. We can go ahead and take that poll down when we're ready. So as we go forward, we're going to start looking at different things when it comes to energy installation and interconnection. I'm going to start by giving us an overview of the military perspective on what this takes. Then we're going to go to Bill Taylor with ESG, and he's going to give kind of deep dive for us into developing energy resilience from an ESCO perspective. And then Michael Higginson is going to wrap that up for us. We're going to talk about cogeneration and microgrid interconnection. So starting with the military perspective, energy projects are complex. Utility interconnection projects are complex. When it comes to DoD energy installations, there are a lot of other considerations that need to be evaluated. So let's talk about why the military thinks differently about resiliency. what happens to a military installation when power is lost? What critical operations need to be maintained? What facilities need to be maintained for those operations to continue? What about flight lines? Deployment of assets, whether these assets are aircraft from an air station or an air carrier, ships or submarines from a naval base. What about control centers? Control centers that are monitoring foreign and domestic affairs. All of these need to be taken into consideration when we're talking about resiliency on a federal or military installation. So when we talk about all of these operations, how are they impacted by outages? Anyone who's been involved in a planned outage at a federal installation, military base, understands that this request or procedure that you have to go through is quite a process. Planned outages can take weeks, sometimes months of planning in order to take that outage. So if planned outages take that much planning, how does an installation respond to unplanned outages? So it's important to know that it's crucial for systems to be in place so that installations can react quickly and efficiently so they can maintain the critical high-level operations that are necessary for our national security. I want to cover just 3 kind of main areas for consideration when we're looking at these mission critical facilities: redundancy, resiliency, and security. Starting with redundancy, there are multiple levels that we should consider. Starting with evaluating the installed infrastructure, including existing infrastructure, and also looking at newly installed infrastructure or updated infrastructure that may be part of the larger energy project. We need to ensure that they are technically viable for the energy application. Sometimes asking a simple question of, can the infrastructure receive the new technology that we're trying to bring to it? Some can, some cannot. If it cannot, are there plans for that to be upgraded? How is that going to overall play a role in the redundancy when we're looking at a main installation? Next, looking at the control system. The control system needs to be considered with the overall infrastructure and the long-term operational goals of the energy project or the installation, such as a microgrid. Why is this important? When we looking at the installed infrastructure, existing, possibly new infrastructure, looking at the overarching control system, long-term operational goals, whether that be new infrastructure, new equipment throughout the base, or are we looking long-term at a microgrid? Why is that all important when we're looking at redundancy? We need to avoid a single point of failure. And we need to avoid that single point of failure, not only within the installed infrastructure, but within the control system and the overall energy project. So next, let's move on and talk a little bit about resiliency. Resiliency at a federal installation is more than the simple addition of a backup generator. Installations look at their existing assets. They evaluate the addition of new assets, whether that be distributed energy resources or new infrastructure, such as switchgear or air brake switches. We may look at energy storage implementation, solar PV, generators, whether that be diesel generators, natural gas generators. And a little later in the presentation, Bill's going to talk a little more about the requirement for installations to remain operational after an outage. But I want to talk about a specific example, about a 14-day requirement for an installation to remain operational after an outage. I'm going to use the example of a diesel generator. The questions that the base has to start asking: do they have enough fuel to maintain that 14-day time frame? What about storage? Do they have the storage facilities? Let's go a step further. Do they have enough real estate for the fuel storage? So that's just one example and some things that we talk about with resiliency when we're looking at these mission critical facilities. And lastly, let's touch briefly on security. These installations are protecting against threats, domestic and foreign. So first, let's look at physical security. If you've ever driven up to an installation, a military base, however you want to term it, did you walk right in? I'm guessing not unless you have the proper credentials. You're going to walk up, you're going to see fencing. You're likely to see guards posted at the entrances. possibly throughout the perimeter. There's also a process that you have to go through in order to walk through those gates. You have to be approved. You have to make sure that you have your proper passes and your proper credentials. So these are the physical barriers that we start with. Next, we want to talk about the security of the installed infrastructure, existing and newly installed equipment. So equipment hardening and protection, that needs to be considered when we're looking into network designs and controls configuration. Which then all leads up to lastly, but definitely not least, is cybersecurity. Believe it or not, cybersecurity is not just a buzzword, and it must be considered at the initial phases of an energy project. This is going to allow the appropriate time frame to go through the risk management framework. You may have heard that as referred to as RMF process, and that allows enough time to properly identify the critical systems in order to receive the authorization to operate from the DoD. So as we take these high-level items into consideration, we can start looking at what it takes to develop energy resilience. And for that, I'd like to turn this over to Bill Taylor with ESG.
Thank you very much, Emily. Can we go to the first slide? There we go. Great, thank you. And the next one. Great. Emily talked about the different functions that can be on a military installation, and they do vary, depending on where you are in the country, depending on the branch of the service, depending on a lot of variables. But that function, that mission is why that base exists. If they didn't have a mission, that base wouldn't be there. So we start with what's the mission? When you talk about resiliency, when you talk about making sure that that mission can be accomplished in the face of an outage, of a utility outage of any kind, not just power, natural gas, water, etc. What's required to achieve the mission with the minimal amount of impacts? She said, yeah, it takes a long time to plan, to have a planned outage. An unplanned outage happens in milliseconds. They have to be ready. What type of disruptions do they want to guard against? Hurricanes, if they're on the coast, tornadoes perhaps, cyber attacks, malicious acts on the infrastructure. All these become a question of, okay, the mission must continue, but under what circumstances? What are we going to guard against? And the other question to ask as you start to fill out the mission and you start to begin to understand what they're doing, you need to understand the extent of what the mission encompasses. There could be several hundred buildings, usually are, on a DoD installation. A subset of those are required to execute the mission. How are they connected? Where are they? Where are they physically located? Are they not in close physical proximity? Are they in electrical proximity? Are they in proximity for the water? You have to understand and take a look at how is the base laid out, where are the critical functions, and how do you deal with that? The other question you want to ask yourself is there energy flexibility? Emily correctly stated that at least two of the branches want 14 days of continuous operation in the event of a problem. Is there any flexibility to that? Is the requirements for power and water and wastewater, et cetera, on day one the same as they are on day 14? Is there a sliding scale? Does it suddenly go down to zero once they start to move the functions a little bit? These are the types of things you want to understand about the mission itself. Emily, next slide, please. So where do you start with resiliency? You want to understand all the questions from above, but now you want to understand of how they wish to approach that. What are the requirements for resiliency? Understand the problem. What are the needs to make sure the critical functions are maintained? Most military installations will grade their functions of each building, 1, 2, 3, high, medium, low, critical, non-critical, uninterruptible, interruptible, etc. They have a continuity of operations plan in the event of a problem at the base, utility or otherwise. What's their continuity of operation plan? They may not be able to tell you, but they can give you parts of it. That's the current state. You want to understand what their future state wants to be. You're looking at severe weather events. You're looking at, bad actors. What is the most critical need? Do they have all the critical buildings backed up with diesel generators? Okay, then maybe they're all set. Do they have a logistics plan to bring fuel on base? Do they have enough storage? With the questions you begin to ask about where are you now, where you want to be, you learn what they're trying to solve for. The gap between where they are today and where they want to be is the gap analysis. The requirements you derive will come from that gap analysis. This is where they want to be, this is where they are, what's the difference? That's what your requirements become. Oops, go back one more. There we go. But understand the requirements are unique to each facility and each function. Hey, Emily, go ahead, please. Gap analysis is the driver for energy resiliency. Focus is usually on providing power. Don't forget the other supporting functions, water, wastewater, key facilities. Something as simple and mundane as traffic control. You have these large bases. People are going to be moving back and forth. This is an emergency situation. Traffic control is going to show up. At some point, that's going to arrive. Things like that will occur. Security lights, cameras on the perimeter. You ask them, what's your current resources? Distributed generation. What kind of controls? What kind of cybersecurity requirements? Do you have portable power? Do you have stationary backup power? Do you have central utility plants? What do you have on base that we can actually use to help generate resiliency? How will the resiliency be managed? We go through a complete series of use cases, go through the analysis of how are we going to operate the base? How are we going to maintain it during a power outage, during a utility interruption? That analysis, all of this analysis has to be collaborative, not just within the ESCO, the Energy Services Company, but within the military as well, within the base. If they have a utility privatization entity on the base who manages their utilities, their wires, et cetera, the electrical distribution system, they need to be involved. More than likely, utility will have to be involved. This becomes a collaborative design effort of all the stakeholders to come to the correct solution. Next slide, Emily. When you start looking at it like in a holistic fashion, you start to get the big picture. You don't need detailed requirements right now, but you do need to understand where they want to go, where they are, where they want to go. Treat the resiliency as a system. Look at it holistically. When you look at it as a system, then you can begin to drill down into subsystems. You can begin to break the design down into manageable pieces. You can begin to develop a roadmap. They may not be able to do it all at once. You may want to do it in phases. You can begin to develop that as you go further. You want to identify the global issues, get down to very specific. You want to look at the interfaces, electrical distribution system, not just on site, but the local utility, which gets into interconnection. Natural gas distribution system, the other pressures you need. You have the distribution lines you need to put the generation resources you're going to add in the right spots. Water, wastewater, is that all off-site? Is it on-site? Are the resources available? Do you need to store it? What's their communications? Their fiber optic network. Do they have fiber strands that aren't being used? Maybe, maybe not. Or do you have to run your own? That has implications both in cyber as well as in the cost. What kind of control data you want to have? What's your SCADA system look like? Finally, as Emily mentioned earlier, the cybersecurity, the RMF process. Next, please. Once you start to put the design together, you need to integrate. You're going to add probably some distributed energy resources. What's your fuel consideration? What's available? Do they have something on site? Is it an airfield? Are they using aviation fuel? Can you use that as a backup? Do you want to run with natural gas? How do you want to run with it? Are you going to use renewable energy? If you do, how are you going to manage the power when there is no renewable energy? How are you going to bring it online when there's a power outage? What's forming the local grid? Are you going to use portable generators? Great for very quick responses. Are the buildings equipped to take that power? Do you have the diesel on site? How often do you have to refill it? What's your logistics methodology for refilling those throughout the day, throughout the week, throughout the 2 weeks? You can interface behind the meter, which is typical. You can also interface in front of the meter to some degree by putting what's, an enhanced use lease. You can build a system outside a peaker plant, a generation resource for the utility, but And the DoD has offered lease for in-kind services of land that they own to put that on. And so that's an enhanced use lease in a nutshell. So you have that ability as well. So there's a lot of different ways to integrate with the facility. Next one, Emily. Okay. What are the time requirements? If I lose power, how fast do I have to restore it? There are buildings, particularly command and control, that are going to say, I don't lose power. I don't have a blip in my power, and my voltage don't ever drop in my frequency. I have a steady system. So they have what an uninterruptible power supply. It'll be seamless. They'll have enough battery backup that seamlessly comes online, much like you have on your computer, usually under your desk. There's a little battery pack there. It allows you to continue to run when there's power loss until you can shut down. Well, these are going to run until they can bring the distributed generation online. Then that'll come up, the battery will see that it's prime power, and they'll shut down. If you have minimal disruption, say less than 5 minutes, you probably will have another battery, but it won't be uninterruptible. It'll be a slightly different inverter, different function. It'll recognize the voltage drop. It'll come online in probably a quarter of a second. But enough of a time lag will exist where the lights are going to blink. HVAC may restart. You're going to have some notification that, hey, the power just went off. Because reciprocating engines, turbines take longer, but most reciprocating engines, diesel's about 5 minutes, natural gas a little bit longer. How can you block load them? How do you bring them online? You start to ask an awful lot of questions. But the other thing to remember is the shorter the time for restoring power, more than likely the costlier the system. Next one, Emily. Gets back into control. We're starting to peel the onion a bit more. What type of controls do you want? What does it have to do? Is it a tiered architecture? I'm going to do this, this, and this from a master controller. Am I going to do distributed architecture? I'm going to be PLC based. Probably the generation will be PLC based. You want to command and control that from something else? It's going to be PC based, where I have a software program. I'm going to use a component or a master controller as the main driver of my controllers. Am I going to have it so that if I lose my, quote, master controller, another one picks up those functions in line until that one's available again? Do I have distributed control capability, as Eleanor mentioned earlier? All of these are viable. Every one of them works. So what's going to drive your choice? Next slide, please. Requirements. Always go back to requirements. What functions does a control have to do? Call it a microgrid controller for now. What's it going to do during normal operation? Base is running normally. Am I going to peak shave? Am I going to participate in demand reduction programs with the local utility or the ISO? What's my normal functions? What happens during an island event? What's going to happen there? What functions have to occur? I've recognized the utility's gone. I've closed the circuit breaker. I'm now island mode from the utility. What does that controller have to do? Is it going to do a heartbeat? Is it going to continually check my status of my system, or the microgrid system, the redundancy system, the N+1, everything that I need to make the base run? It's going to continually check to make sure that when that island switch is thrown, everything works. What data inputs do I need? I need probably total kW. How many watts am I drawing? Power outage, I need to sense it. Health check, like I just mentioned, error codes, human machine interfaces, and there's a lot of others. But on a DoD installation, how do you get the data? You're not going to have two-way communication off-site. Maybe you can get one way, maybe. And that's one way. It's probably going to go from the DoD installation off-site. How do you manage on-site? Think of the perimeter as a barrier, not just for humans, not just for physical entities, but for the cyber, for the communications, for IT. It's a barrier there as well. You're not going to take data off-site typically. So how do you do that? Where are you going with that? You have to plan ahead. Next slide, Emily. As you're thinking of all this, you go, okay, I've got this. Normal operation, I'm going to do this, A, B, and C. In island mode, I'm going to do D, E, and F, and G, and everything's good. That's two use cases for all intents and purposes. What happens if something goes wrong in the middle of that? I go to start a distributed generation resource. It doesn't start. What if I have a glitch in my battery inverter and I can't form a grid with the solar on site? What happens if? And you start to go through those questions. It's not just a mind experiment. It's just not a thought experiment. You can go through fault trees and fault analysis and all that stuff. That's great. However you wish to do it. But the fact of the matter is, there are probably going to be several hundred what-if use cases versus 2 normal ones. The what-if use cases will drive the design of the controls. It will drive the design of any microgrid system that you have as you begin to protect. How automated does it have to be? The more automation, the more use cases you're going to be looking at. And that's okay. As you develop that methodology, as you dive deeper and deeper into that design, remember a couple things. You want to design the diagnostic instrumentation in originally. You do not want to add it later. If you have a fault condition, you want to know about it, whether it's in test or whether it's in reality. You don't want to have to go looking around for the problem. You want the problem to say, here I am. I'm right here. Come fix me. So as you design the control system, as you design the DERs, as you design the resiliency from a holistic standpoint, think about what's going to happen if something doesn't work correctly. Think about what's going to happen and how you're going to fix it and how quickly you're going to fix it. You're now in a non-normal situation. Power's been lost. Something's wrong. How do you deal with it and how do you deal with it quickly? If you have a problem in your system. When you look at that, you say, wow, okay, I need a very, as I talked about collaborative design before, it's a very coordinated design effort between ESG, the facility, the utility. You have no option. That is a must. They all must be on the same page at the same time as you design the system. Next slide, please. Window cybersecurity. I said earlier, getting two-way communication or even communication one way off the base is at best difficult. Can be done, but it's difficult. Two-way communication is much more difficult. What are the cybersecurity requirements for your system? Okay, you're putting a new entity on here, resiliency. It's called a microgrid. That has its own cyber. How can it be attacked? Where can it be attacked from a cyber standpoint? That control system must be cyber secure. Because what could happen? You lose power, it gets attacked, you don't have resiliency either. Again, another use case you look at. Data links is not just the command and control needs to be secure, the data links must be. If you're going to pull KW off a meter that's on base, that data link must be cyber secure. If you're going to pull in health data for the components from reclosers, from DERs, from distributed energy resources, from the solar field, from the battery, you're going to make sure everything is functional 24/7, 365. That's got to be cyber secure as well. What are you going to do with that data? Send it to an HMI? That's great. Now what are you going to do with it? Who looks at it? You can't really send it off-site. That's probably not going to occur. What do you do with it? How do you analyze it? How do you set an alarm condition? These are all become secure questions. One other thing, most of these bases are very large, very large. Some are measured in miles between where the microgrid is going to physically exist and where the HMI is. You're going to run fiber between there? What's the communication level? Can you run fiber between the two? If so, how is the fiber secured? Is it overhead? Probably not. How are you going to run that fiber cable and be secure about that? Not just cybersecurity now. I got to run a cable. I now need physical security. Look, as you begin to peel the onion back deeper and deeper, these are all questions you're going to have to answer. Next slide, please. Go back again and just reiterate. Review resilience holistically. Treat it as a system. Look at it in general and drill yourself down as far deep as you need to go for the design. It is a collaborative design. The ESCO, in the services company like an ESG, the DoD facility, the private utility, the utility privatization contractor on base, the outside utility. All of these people must collaborate. You have to understand the requirements, not your solution. You're not coming in there with a solution looking for a place. You're designing your solution to meet the requirements. Big difference. Because every requirement changes. You need to make use of available existing options. Do the gap analysis. Look around, see what you've got. You can electrically group buildings even better. If I can power a whole substation circuit rather than individual buildings, it's even better. Because I can localize my generation. Use cases are going to really define not just how it's going to be operated, but how you're going to design it. Cybersecurity, you design that in. It's not an add-on. It's not something and then, oh, I forgot. Nope, you design it in. When you begin the design, you begin the cybersecurity design at the same time. With that said, the controls need to be flexible over time. Conditions change, missions change. The mission of the base will change. Technology changes. Everything's got to be flexible. As you look at, as you're doing this, just add one more bit of complexity. When you take a look at the designs, a lot of the engineers are going to start with the nominal design, usually called the steady state design. This is where I'm going to design my system. But there are limits to that design. There's going to be changes to that design every single day from the environment, from how the equipment is operated. Is there a fault somewhere in the electrical distribution system? Does the natural gas or the diesel have some contaminant in it? Steady state designs aren't planned for that. They're going to change. Next slide. I think this is the last one. One last comment. As this design is going together, the controls, the piece parts, they have to be simulated, and far more than simulation. You're going to test every use case in simulation. You're going to test every what-if use case in simulation. But as you go through the simulation, you're going to begin to add the real PLCs, the distributed energy resources. You're going to begin to add the reclosers. You're going to begin to add every subcontroller you have. You want to test against the real hardware as much as physically possible. You're going to do detailed factory acceptance testing. You're going to build that up gently. You're going to add to that. Because only when you know all the subsystems, only when you know that they all function, are you going to do the whole microgrid decommission and turn the base power off. That is difficult to do. And it takes a lot. You do not want to do it a lot of times. You prefer to do it only once. You want to find your issues early in the build cycle, in the design cycle. You want to find it early in the testing cycle. It costs you a lot less money, and it causes the DoD base a lot less angst. You really want to put that up as far as you can. Right? The only way in final commissioning, minor issues, no problem. Major showstoppers never should be there. They have to be found way up front. A model that I tend to use, if it hasn't been tested, it's not going into that system. It's not going to happen. All right. I believe next is Michael, and I believe there's a poll in between, if I remember correctly. Thank you so much for attending. I do appreciate it.
Yes, you're right. And thank you, Bill. So let's start this section by checking in with you, the audience, and hearing your experience with generation interconnection. On your screen, you should see a poll popping up here. It's intended to get a feel for your experience with these types of projects. There are a few options. Please check all that apply. While you're responding to the poll, if you have any questions based on what you've heard from Emily and Bill so far, or what you hear from me coming up, please enter those in the Q&A button on the bottom of your screen. We'd be happy to address your questions shortly at the end of this section. Let's see what your experience is like. Let's see those poll results. Oh, great. It looks like I'm glad to see some of you have experience with interconnections already, and what you hear in this section might resonate with you. For those of you with less experience, I hope to shed some light on the interconnection process for microgrids and how it can benefit all the people involved. In the past sections, you heard about how it's critical to understand site operations and how resilient systems are developed. These projects involve interconnecting generation and/or energy storage systems to the utility system. In this section, we'll discuss what goes into the interconnection process and how collaboration between the energy service company and the utility can lead to mutual benefit. Energy service company is commonly abbreviated as ESCO, which I'll be using throughout this section. SNC's experience with both ESCOs, DoD facilities, and utilities enables us to understand the perspectives from all sides. And we really want to see all parties benefit from DoD microgrid projects. First, we'll start with an overview of the interconnection process. Throughout this section, we'll refer to distributed energy resources. Often you'll see this abbreviated as DERs or DERs. This includes generators and or energy storage systems. It's more than distributed generation, it also includes storage. We will dive into distributed energy resource sizing and location, which are two key factors for interconnection. Then we'll go on to discuss the steps in a typical project's interconnection process. Next slide, please. Two of the most important considerations in the interconnection process: sizing and location. The size in megawatts of the resources interconnected, and the location being where these new resources are going to go. It's common that the resources used on these projects are multiple megawatts, sometimes even over 10 megawatts. With large generators and energy storage systems of this size, their impact to the local power system can be significant. For example, we can impact short circuit levels locally as well as power flows on the local circuits. The physical size of these resources can also be quite large. We have to find an appropriate and safe place to locate the resources on the project site. Next slide, please. Now, let's overview the interconnection process. As we just covered, the first tasks are to identify the size of the resources we're going to interconnect and where they're going to be located. Once there's a concept of the size and location of the resources we're going to interconnect, a prudent next step is to start discussions with the utility. This discussion can cover points of interconnection and circuits we could be interconnecting with. Often DoD facilities have multiple circuits serving them to ensure reliable power supply to their critical loads. Interconnecting to a specific one of these circuits might have advantages. And based on the discussions with the utility, the design can iterate to develop the most effective design and connect to the best circuit and the best location for the project to succeed. A formal interconnection application must be applied for in the design phase. And often this process can be lengthy, so starting early is usually best practice. Since we have already had initial discussions with the utility at this point, we can be more confident that the application is going to be approved and going to be successful. Once the interconnection application is completed and approved, the interconnection itself can proceed. This interconnection can include upgrades to the local power system, for example, some protection changes, voltage regulator changes, or service conductor size increases that we'll touch on momentarily. Next slide, please. When done well, cogeneration and microgrid projects can provide benefits to all of the parties involved: the utility, the DoD facility, and the ESCO. The benefits to the DoD facility and the ESCO have been discussed by my colleagues in the past couple sections. And in this section, I'm going to talk about how they can be also beneficial to the local utility. Here we identify 4 significant ways that the projects can have and using a collaborative approach to these projects can benefit local electrical power utilities. First, in the top left, you see improving the ease of implementation and integration into the utility system. In the top right, there's providing an opportunity to upgrade power system infrastructure. In the bottom left, new opportunities to provide grid services from the project. And finally, in the bottom right, improving the ease of maintenance and operating the system over the project lifetime. Next slide, please. One significant advantage of collaboration between the utility, DoD facility, and the ESCO is ease of implementation. Through collaborative efforts, we can choose an interconnection location that makes the process go smoothest for everyone. As we just discussed in the previous sections, these facilities have critical loads that are extremely important to maintain continuous power supply, and there are neighboring loads as well. Through the testing and commissioning process, we're often going to need to test the sequences that test that we can successfully restore, which could involve an outage. A well-designed interconnection, when paired with an effective test plan, can minimize the outage and its impact to local customers during installation, during the commissioning process, and during the testing process. If we design the interconnection well in collaboration with the local utility, we can minimize these outage durations and their impacts. Next slide, please. Often cogeneration and microgrid projects require upgrades to the local power system infrastructure. For example, these upgrades can include things like protection improvements, such as directional power measurements at the point of interconnection to measure for exports, or direct transfer trip signals sent by the local utility and received by the microgrid to ensure generation is disconnected if there's a local system fault or a switch opens to avoid undesirable islanding conditions. Other upgrades can include switchgear and breaker upgrades to interrupt increased short circuit levels. As I mentioned previously, short circuit levels often increase when we're interconnecting cogeneration or microgrid generation, as well as storage. With a collaborative project where the utility, DoD facility, and ESCO are all working together, we can take a mutually beneficial approach. What that could look like is interconnecting to a circuit where there are minimal upgrade requirements, or alternatively, if all of the local circuits serving that site or nearby would require an upgrade for the interconnection, we could select a circuit that the utility is interested in upgrading or could benefit most from upgrading. Next slide, please. With cogeneration and microgrid integrations, the generation and energy storage resources, or DERs, we interconnect can also provide value to the external system. What I mean by the external system is outside of the facility where the DERs are installed. This is commonly discussed as non-wires alternatives, or abbreviated as NWA. It gets this name because some of the advantages we can offer with this, or the services we can offer with the DERs on site, can alleviate needs for other power system upgrades, like increasing wire size or conductor size. Some of the benefits a cogeneration or microgrid project can offer to the external system include peak shaving, reducing peak load, voltage control, or reactive power management. Peak shaving can be valuable to local utilities because if we can reduce site peak loads, we can reduce strain on local equipment and potentially defer otherwise required upgrades, such as increasing conductor or transformer size, and thus defer capital investment requirements. If the facility is at the end of a line or on a heavily loaded line, we can also use the DERs to help control the voltage using active and reactive power management of the local energy resources, DERs. If the local circuit needs or could benefit from these services, they could be incorporated into the project, adding use cases that serve and provide value to both the local DoD facility as well as the neighboring community and electrical loads. On the right, you'll see a picture of a utility microgrid that I personally have worked on, which provides a variety of these services to the local system, including peak shaving and voltage control using reactive power management that I mentioned previously. You can see over on the right here, there's a variety of resources that are combining to offer these services, including wind turbine, generators, energy storage in the bottom right-hand corner, and solar photovoltaic panels across the right-hand side. Next slide, please. Yet another advantage to collaborative interconnection process is improvement to future maintenance and operations. Many times utilities are responsible for maintaining equipment on the base, on the facility, DoD facility, or nearby. In the case that they're responsible for maintaining this local equipment, it's best if the utility is engaged in the system design and the interconnection design. This collaborative process can help ensure that the utility is happy with the design and they're able to operate the system going forward. To the extent it's practical, it's best to keep the microgrid equipment consistent with local utility equipment and also their practices to ensure it will work well for the utility personnel. Utility operations may also be impacted by the presence of a locally islanding system. Specifically, it's common that we de-energize electrical power equipment before we work on it. As I'm sure you all know, electricity can be dangerous and de-energization of equipment can make work safer. If there is a system that can island and keep equipment energized after the utility has been disconnected, it's important that utility personnel understand this and are aware of how this is going to work. This understanding and awareness can ensure that the utility personnel can work safely on the local equipment and also avoid damaging equipment by unintentionally closing in when something is energized. A collaborative engagement can ensure that the system is designed to streamline future utility maintenance and operation. Next slide, please. In conclusion, thank you all for joining our webinar today on DoD energy installations and utility interconnections. We hope you appreciated hearing our insights. In conclusion, we hope you take away the following key insights. First, that understanding critical facilities and their operations is key when evaluating resiliency implementation. Next, that resilient systems and resiliency itself must be viewed holistically. Steady state systems aren't always steady state. And what if contingency use cases can drive the microgrid and controller design and development? Finally, when the facility, the ESCO, and the utility all collaborate, everyone can benefit from installation of cogeneration microgrid resources. If you have any questions, please feel free to type them in the Q&A section. I look forward to answering your questions, and feel free to reach out to us after. Thank you, and I'm passing it over to Spencer now to handle Q&A.
Thank you again, Michael, and thanks again, Emily and Bill, for sharing these fantastic insights today. As Michael mentioned, as we move into the discussion part of our webinar, I want to remind everyone in our audience to please use the Q&A function at the bottom of your screen to post any questions you have. We have a lot of questions in already, so I'm going to start with some of the ones that some of our attendees started with early on. So first question is there any data or case studies on power outages at DoD facilities?
Spencer, this is Bill. I can add something to that. The local utilities do report outages. They both report frequency and standard duration. Those are available as databases across the nation for the local zip codes and for every zip code, actually. So the DoD can start with that. There's also been a number of cases where they have done black start or basically pull the switch, if you will, and DoD installations. Some of that data is a little bit more difficult to come by, but that data does exist that usually drives upgrades to the facility to make sure how they match it. So I know those two aspects are at least being done on a regular basis. And I believe Congress also said all bases must be tested within the next 2 or 3 years. I think that's the time frame.
Are there any insights of when they say tested, is that information going to be made public by Congress, or is that just something that they're asking the DoD to do?
At least at most levels, that the high level data may be published. The detailed data will not be. That'll all be classified for a DoD facility.
Michael, Emily, anything to add to that?
I think Bill really hit the nail on the head.
I think Bill did cover it. Bill, I believe you're correct. I believe that time frame is within the next 2 to 3 years.
Excellent. Another question from our audience: does the DoD or any of the branches have any preferences in the type of generation they prefer at their sites?
I can start with that, Spencer, and then Michael and Bill, please jump in. We see that vary by installation and by branches, and some of that is based on region, where they're regionally located. what's available, and also what real estate is available. You're going to have some different real estate if we have a base that is inland versus possibly a submarine base that's, has piers and has ports that have to be taken into consideration. So a lot of those, from our perspective and from our discussions with, with different branches, is going to depend on the real estate available and their location. So we see that vary greatly throughout each installation.
The only thing I would add to that, Spencer, is that it also is going to depend to some degree on what the installation infrastructure is like. If they don't have sufficient gas pressure, they're not going to be able to turn on or be able to support certain DERs, if you will, whether it be a reciprocating engine or a turbine. If you're too far north, you're really going to want to use solar. If you're inland, the wind may not be a viable option. So it's, as Emily said, it really is location. It's like a real estate, location, location, location. They also will pay attention to the local state and region they're in, and states will vary on on the type of generation they want to see. Federal installations are generally exempt from those rules, but what we have found is the vast majority of them will follow local mandates. So be careful of what state you're in, take a look around the local laws and what essentially the PUC, the Public Utility Commission, is pushing.
I think that's a good transition to another question we got, which is, does the DoD or any of the branches have any sustainability goals driving the use of more renewable resources at their facilities?
The short answer is yes. They all have sustainability goals. It tends to vary by administration. What they're looking at now is not just sustainability, but net zero. They do want their generation resources to be net zero, carbon net zero. That's pretty much across the board. Again, that'll vary by state to some degree, by installation. You'll see variation by installation commander and by installation energy manager as well. So they all have some variation off of that.
I think.
Sorry, go ahead, Michael.
I just gonna add, I think this dovetails nicely with the last question, and considering if you have a 10 megawatt installation and you need 10 megawatts of solar, that's valuable to aspire towards and useful for sustainability goals. But I think to Emily and Bill's points, we really need to think about location. That's going to take up a lot of space. With any option you go with, the space matters, and because storing 14 days worth of fuel for 10 megawatts of generation is also a lot of space. There's something to be said for the independence of not having to store fuel and to be able to, in theory, perpetually have power from the local solar. I think the other thing that dovetails here and is important to consider is what caused the outage. If you're worried about an outage caused by adverse weather, could that weather also be impacting your local solar installation? Is that going to impact how you need to size it and how you're going to run your facility to make sure you can run for the 14 days that we need to?
Excellent. I think, go ahead, Bill.
Just that thing to that, as you go into and what you're going to see in local, based on states and based on the local utility, as you add more and more solar, you get the duck curve. You get the solar peaks at the end of the day and it starts to drop off at night. What we're starting to see for bases is that when they're subject to a demand charge, that demand charge is shifting from the middle of the day, say from 10 o'clock till 5 o'clock, more towards the afternoon where the duck curve starts to come into place, where the solar power drops off. So you do need to be careful what you add. You also need to take a look at your rate structures you add DER. It may or may not change. There are going to be variations on that based on the utility, based on the state, based on the local laws. So one more variable to keep track of.
Emily, I think the next one is for you. You talked about RMF, risk management framework, and authorization to operate. How long does going through kind of the risk management framework and authorization to operate for the DoD normally take?
It's going to vary greatly by project. It's going to vary with complexity. I'm going to just throw out a range. It can could be this, it can be fall within this, depending on the complexity of the project. You could be looking at a 6-month process. You could be looking at a 24-month process. The point that we want to drive home when we're looking at cybersecurity is we don't want to finish an energy installation and then go, hey, we need to add cybersecurity onto this. Well, if you want to energize in 3 months, guess what? That's not going to happen. That needs to be built into the entire process because it really is something that is considered throughout all of the pre-planning phases, the development phases, in all of the equipment that's going to be utilized, whether that be existing assets, existing infrastructure, added infrastructure, new assets such as DERs like the PV and the energy storage. So that's something that's a process that we can usually identify a timeline once we have enough details about the project, but it can be lengthy. And so we usually see that fall somewhere between the 6-month and 24-month range, depending on the project.
All right. This question, we've gotten a couple different questions related to this, so I'm going to kind of try to sum it up, but I think it's great if like each one of you could talk to it. But got a couple different lines of questions related to natural gas and its role as a distributed generation or just a generation source at DoD facilities. Some claiming that it's more reliable and net zero related to solar and other renewable sources. Can you talk a little bit about natural gas's role in these facilities and their generation on site?
I can start and then probably pass it off to Bill and Michael. I think what you hit on in part of that question, and Bill started to touch on it with changes of administrations. There's always new resiliency mandates. There's new sustainability goals that we're looking forward to. And one that is being considered now across the board is decarbonization. They're looking at a net zero impact when we're looking at installing on some of these new installations. So when they're looking at an energy project in those pre-planning phases and those development phases, natural gas is being looked at from that lens, specifically in some cases for a decarbonization effort.
Yeah, to tie in with that, a couple of the words that come to mind when you think of natural gas systems are efficient and cost effective. And those tied nicely in. When you have efficient systems, you have less waste, lower emissions, and cost effective is often intersecting with a couple different values that we're striving for on these projects. There's often also high volume natural gas supply in areas that can be leveraged, not always, but often. And I know there's movements towards renewable natural gas as a lower carbon solution.
Just to build on both of those, the decarbonization is driving in some states where you cannot put power back onto the distribution lines unless you're net zero. Natural gas is low emissions. You can use it to help defray the cost with the demand responses, with peak shaving, et cetera. But the fact is there are some states that don't like it for a lot of reasons. Renewable natural gas is in its infancy to a large degree. It's being made, digesters make it. High strength organic waste plays into that pretty rapidly. The other aspect of that is renewables have a time limit on them. If you don't, you have a 14-day outage, it's virtually impossible, I don't care where you are, to manage that with just renewables and batteries. We're just not there yet. You have a backup of something. If that's diesel fuel, okay, now you have different air emission standards. So you have to play not just I don't want natural gas, but I have to run these and I have to meet the local air emission standards. The other thing I will say, and I won't go into detail, but there are technologies online, they are coming up online, they're being designed now, that are net zero using natural gas. It's a different form of carbon capture, but nothing gets to the atmosphere. So that does exist. That technology is going to come online very shortly. It already has been online. The test system's been online for about 4 years now. So that is also coming up. So there are methodologies to deal with that. It's just a question of where you're at, and very honestly, in what state, and how aggressive you want to be on technology.
So we're getting close to our end time here. So I think I'll just wrap up with one last question. If each panelist could just briefly share the biggest insight, one idea that they'd like the audience to remember when it comes to DoD installations and interconnections in under 15 seconds. Michael, can you get us started?
Sure. I've got this one ready. And for me, it's straightforward. It's what I wrapped up the presentation with. If ESCOs, DoD facilities, and utilities work together, you can create a solution that really benefits all parties.
Bill?
Be patient. That collaboration, that the checking through the checks and balances through the federal government, you need to be patient. It will get through. It's just going to take a little while.
Got it. Emily?
My last one is remember what we're dealing with when we're losing power at a military or a federal installation. It's frustrating to lose our refrigerator when we lose power, but we're talking about critical facilities. We're talking about maintaining our national security. So it's key to just remember that we're dealing with critical operations and critical facilities at these installations.
Excellent. Thank you again to our panelists. And before we wrap up, as a reminder, we will be sending a recording of this webinar to all those who attended today. And in addition, when you leave this webinar, you will be prompted with a 1-question survey on today's content. We would greatly appreciate a few seconds of your time to complete that question before moving on with the rest of your day. So with that, I want to thank Emily, Michael, and Bill for their time today. And for all those who attended today, on behalf of S&C, thank you for spending your valuable time with us. Have a great day.